Hi, I'm Wyatt on Team Organic Photovoltaic Fiber. Today, we'll show you around the lab the exciting new developments in the Lesco group. Come with me! This team practiced some of the most cutting-edge science today. Here you can see, Espen, what are you making, Espen?
Organic photovoltaics.
Beautiful. Our bright mathematician, Parker, over here. Tony, what are you working on today? Boston Brothers. Nice. And here is our assembly line. Hi, I'm Wyatt.
Hi, I'm Espen.
I'm Parker.
Tony. I'm Wall.
And we're Team OPVF. Here's the assembly line we've produced to come up with a wire-shaped organic photovoltaic. Our core wire starts off here. It winds through a tension sensor which maintains constant tension throughout the process. It goes under a waterfall of an oxide layer which is then cured in an oven. The wire then follows under a coating of the active layer and is cured again before being wound on the final spool. Our design is modular so that you can implement as many coating stages as you want for whatever material. The exposure time and the concentration of the solution determine the thickness of each layer, and the oven spacing determines the annealing time of the layers.
As the wire leaves the tension sensor, it undergoes the first waterfall where it receives its electron hole transport layer, in this case a TIOS. This is the first pump module. It's a little bit higher power because the TIOS layer is a very viscous layer. It goes on the wire right here before entering this oven and being subjected to another coat of the active layer, a bulk heterojunction of P3HT and PCBN, which is much less viscous and thus requires a less powerful pump. Both pumps are controlled by this Arduino-based microcontroller circuit, which can switch the voltage on or off to each pump, which is a 12-volt peristaltic pump. Here the user can select the different amount of layers to coat and start and stop the coat. So the wire enters through this first window here to be annealed at around 110 degrees C before being redirected by these pulleys, subject to another coating, cured, redirected again and onto the final spool. The temperature of this oven, like I said, is about 110 degrees, and it's constructed of steel and some refractory material made by my partner Wyatt. The oven control unit is right here. It has a temperature controller which utilizes a PID algorithm, which basically continuously takes new bounds to center at one set point and maintain that set point. It's very simple. There's an on and off switch, a user interface, and this relay here takes wall power and switches it on and off to the heating elements, which are continuously switching on and off to maintain the temperature. Thermocouple comes from the inside to give the current temperature readings for the user and for the PID algorithm to maintain temperature.
So I designed the linear actuator and the spool carriage, the tension sensor, and basically the software to get the motors running. In essence, this motor will always be at a fixed RPM. That motor will always be using the tension sensor essentially as a feedback loop. And technically these motors, which are inactive at the moment, will help track the wire so that it's on a continuous strand. Other than that, these are the control drivers and the Arduino Mega board, and it's a whole bunch of wires right now, but eventually it'll look really nice. Other than that, have fun.
Hi everyone, so I designed and manufactured this board. The reason this is such a strange shape is so it could fit inside the fume hood. And I also designed the layout for each and every component with aluminum T-slots because aluminum T-slots are very versatile and modular.